this point, the first 18 agents in our framework have operated in the dark. They process language, query databases, and generate code, but they do so entirely through text. Imagine a standard office desk. A textual description might accurately note the presence of a laptop, scattered papers, and a coffee cup, yet it fails to convey that a drawer is left half open, or that the coffee cup sits precariously at the absolute edge of the desk, ready to fall. If an agent relies on an intermediate model to caption an image before it begins reasoning, the pipeline has already failed. Translating raw pixels into summary sentences results in immediate and irreversible information loss. Systems restricted to text cannot natively process continuous physical phenomena. They are blind to the spatial density of pixel arrays, the rhythmic prosody of audio waveforms, and the asynchronous signals from physical sensor meetings. Agent 19 resolves this limitation. The Vision Language Agent directly ingests raw, uncaptioned pixel arrays alongside natural language instructions, computing a joint probability distribution over both modalities at the same time. There is a sharp distinction between reading a description of an environment and perceiving the raw signal of that environment. By accessing the signal directly, the model preserves the spatial nuance required to notice subtle details that the user never explicitly queried. For an autonomous system to operate effectively in the physical world, visual perception cannot be treated as an afterthought. It must function as a first-class native input. While raw vision language models demonstrate impressive fluency, their architecture often struggles with deterministic tasks. They excel at recognizing broad semantic contexts, but frequently fail when asked to count dense objects or verify minute spatial details. A model will correctly identify the lighting, mood, and layout of an industrial warehouse. Yet, when asked exactly how many shipping containers are stacked in the far corner, it will often guess and state an incorrect count with absolute confidence. In an enterprise environment, a plausible but factually incorrect assertion is dangerous. If an agent hallucinates a clear safety inspection on a damaged structural beam or misidentifies a lesion in medical imaging, the system creates active operational risk. The engineering requirement is clear. We must design an agent that retains the semantic reasoning power of a large language model, while forcing every spatial claim to be anchored in verifiable visual evidence. To solve this, we construct a 4-stage pipeline. This architecture actively bridges the gap between probabilistic visual reasoning and strict deterministic verification. We structure the solution using a dual system model, dividing the labor between a probabilistic engine and a deterministic one, a setup we can think of as the poet and the accountant. The vision language model acts as the poet. It provides the necessary nuance, reading the room, understanding the context of the image, and synthesizing a draft analysis of what it sees. A dedicated deterministic object detector acts as the accountant. It intercepts the VLM's draft claims and cross-checks them by running rigid boundary box counts and coordinate verifications. This division of labor enables what we call the squinting agent. When the primary model recognizes that the visual evidence is too ambiguous or low resolution to make a definitive claim, it triggers a tool call instead of guessing. Using a think, act, observe loop, the agent writes a Python script on the fly to crop and magnify the blurry region of the image. It literally takes a closer look, refining its input before committing to a final answer. A standard model acts as a passive observer, accepting whatever resolution it receives. By contrast, an active perceptual agent manipulates its own intake to eliminate uncertainty. This operational logic maps directly to the 4-stage architectural loop of Agent 19 shown here. Stage 1 is the visual encoder. It ingests the raw image, slicing the pixel array into fixed geometric patches, typically 14 by 14 pixels, and flattens them into dense numerical representations called visual tokens. The choice of encoder dictates the agent's baseline capability. An encoder like SigLIP is trained to tightly couple visual and linguistic representations, making it ideal for language-aligned retrieval. Alternatively, a Dino v2 encoder uses self-supervised learning to produce spatially rich features, prioritizing dense predictions like depth estimation. Stage 2 is the alignment bridge. Because the visual tokens exist in an entirely different mathematical vector space than language tokens, they require an optic nerve to connect them. An alignment mechanism, often a learned multi-layer perceptron or a Q-former, projects the raw visual embeddings into the language model's token space, making the spatial data mathematically legible to the reasoning engine. Stage 3 is the LLM core. Here, the system executes cross-modal attention, calculating the relationships between the natural language prompt and the newly aligned visual tokens. Because the LLM accesses the visual tokens directly, it can ground its reasoning in the physical evidence. It retains the geometric layout and subtle visual contradictions that a text summary would have discarded. Stage 4 is the validation gate. Before the LLM finalizes its output, its draft claims are routed to the deterministic detector for a strict numerical and spatial audit. If the detector finds a discrepancy, for example, the VLM claims there are 3 people, but the detector only finds 2, the safety gate triggers a regrounding loop. The system forces the LLM to reevaluate its claim against the actual pixel data. In high-stakes production pipelines, an agent cannot be allowed to act on unverified assumptions. This gate ensures that abstract logic aligns with physical reality. This 4-stage pipeline provides the structural reliability required for vision agents to operate in high-stakes production environments. We can trace these 4 stages directly into the Python implementation. This code editor shows the vision question answering agent class, which instantiates the pipeline. The initialization logic begins with the auto processor. This handles the stage 1 and stage 2 duties, taking raw pixels and executing the multimodal alignment required to prep the inputs. Next, we load the foundation model, in this case, Lava for conditional generation. To manage the massive computational overhead of visual attention, the system loads the weights in float 16 mixed precision. The agent doesn't simply pass the image to the model. It constructs a highly structured prompt, explicitly injecting a chain of thought instruction that forces the LLM to write out its spatial reasoning step by step before answering. Once a draft response is generated, the validation function takes over. It parses the chain of thought output and compares any quantifiable claims against a hard-coded object detection pass. Because physical sensors can fail or return corrupted data, the execution method is wrapped in a graceful fallback decorator. If the agent receives a null image array, it catches the type error, logs the failure, and safely retries. The alignment bridge and validation gate exist as discrete, auditable functions in the codebase, translating architectural theory into executable Python. This architecture enables 3 deployment categories: parsing complex layouts in document intelligence, flagging defects in industrial inspection, and parsing interfaces for UI automation. Processing dense pixel arrays is computationally expensive. To maintain a strict latency budget in these environments, engineers apply image resolution scaling to reduce token counts and patch pruning to drop uninformative background regions dynamically. Regardless of the specific optimization used, the agent's output must pass the validation gate. Accuracy verification remains the non-negotiable requirement for deploying these systems into the real world. By anchoring its language outputs in concrete, verified visual evidence, Agent 19 establishes the critical perceptual layer required for all downstream embodied intelligence tasks. With the vision language agent, we have bridged the gap between raw textual reasoning and the physical world's densest data stream. But vision is only the first dimension of perception. The agent can map physical space, but it remains deaf to temporal audio patterns and numb to the continuous influx of environmental telemetry. The architectural patterns we explored today, encoding, alignment, and validation, are detailed extensively in Imran Ahmad's 30 Agents Every AI Engineer Must Build. These exact same principles govern the next tier of multimodal perception. Agent 20, the audio processing agent, applies this alignment logic to the cadence, pitch, and prosody of human speech. For 18 agents, we engineered systems that reasoned entirely in the dark. With Agent 19, the machine finally turns on the light.